We want to review for our momentum test on Friday. We're going to start with the very first topic in that unit, and that is momentum. Momentum is a vector, as you know. Okay, momentum is a vector, which is a product of mass and velocity. So we need direction with velocity, which means we need signs. Now, I don't have an example problem here for momentum, but you're going to see as we go through this entire sheet of practice problems that whenever we're dealing with momentum, we need to pay close attention to signs. There's a bunch of places in there where I try to trick you by putting opposite directions, where some of them should be positive, some of them should be negative. Always be conscious of signs. That's going to rear its ugly head on Friday, I promise. If you're not paying attention to signs, the fact that momentum is a vector, you will mess up on Friday's test. So, momentum is a product of mass and velocity. It is a vector, and the units are kilograms meters per second. Now, what's really important about this unit, okay, we start talking about the important stuff when we start talking about impulse. Impulse is the change in momentum experienced by something. Delta P, the change in momentum. It's equal to m times delta V, but it's also equal to F times delta T. Now, impulse is a vector as well. If momentum is a vector, then the change in momentum has to be a vector as well. So if we're solving for the impulse, or if we're solving for anything else in that equation for that matter, we have to pay attention to the direction of the velocity, which is, by the way, not the velocity, it's the change in velocity. Don't ever put just V in there. Okay, that's momentum. M times V is momentum. M times delta V, the change in velocity, the final minus the initial, is impulse. Don't forget the signs for VF or VI. And of course, for the force as well, if the force is to the right, we make it positive. If the force is to the left, make it negative. Okay? Be consistent with your signs, and you should be good. Now, a couple of words of caution here before we actually do an example with impulse here. When we're using impulse, we're looking at one object. There may be 2 or 3 or 4 objects involved in the problem, but when you're solving for impulse, make sure that you're analyzing one object only. If there's 2 objects, that's fine. Pick an object and analyze it. For instance, in question number 1 here, we've got a soccer ball that's moving towards a man's foot. We got 2 objects here. We got a soccer ball and we got a guy's foot. Pick the soccer ball or the guy's foot, one of the two. We know more about the soccer ball, so let's go with the soccer ball. Okay? But in the end, if we knew something about the guy's foot, then we could analyze the guy's foot, because if the soccer ball gains momentum, then the man's foot will lose exactly the same amount of momentum. The impulse, the magnitude of the impulse on the soccer ball will be the same as the magnitude of the impulse on the guy's foot, just opposite direction. So what do we got here if we're analyzing the soccer ball? We got a soccer ball with a mass of 0.430 kilograms. Maybe we want to convert that grams to kilograms. We've got an initial velocity of 12 meters per second. We've got a final velocity here of what, 15 meters per second? And we've got a time of contact here of 0.400 seconds. We want to find the impulse, and we want to find the magnitude of the force of impact. Is that right so far, by the way? Have I missed anything? Can we? Exactly. That's what we were just talking about, right? We missed the direction. We didn't pay attention here to the fact that the ball was moving toward the man's foot. Now it's moving away from the man's foot. If we miss that, this question is wrong. Both parts of it will be wrong. We're going to make one of them positive, one of them negative. It doesn't really matter which one. Okay, when I did this, I chose to make the VI negative. Coming towards me was negative 12. You could have just as easily done it the other way around, as long as they were opposite signs. All right, we're going to solve this now, solving for the impulse. We're going to say it's going to be equal to m times delta v, which is 0.430 times delta v, vf minus vi. Not 15, not 12, but rather 15 minus 12. 15 minus, Matt? Negative 12. 15 minus negative 12. Just because we have a minus in there, VF minus VI, doesn't give us any indication of direction. We have to stick the negative in there because we made it negative. It's opposite in direction. We do the math there, by the way, that works out to be 11.61 Newton seconds, or to the right number of digits, it would be 11.6 Newton seconds. Or you could have said kilograms meters per second. That would have been fine as well. Had you defined VI as positive and VF as negative, you would have gotten negative 11.6, and that would have been fine as well. It's just consistent with the way you define positive and negative. Now, if you want to find the force, we can either set F times T equal to M times delta V, or since we already found delta P, we can just do this. Delta P is equal to F times T. So remember, we're separating it here, but we could just as easily combine these two equations, M delta V equals F times delta T. We know what delta P is. We're looking for F here. Just rearrange it. We get 11.61. You want to use your unrounded number there, and delta T, of course, is going to be 0.400 seconds. We solve for the force there, and it works out to be 29.0 newtons. And once again, if you had made VI positive and VF negative, you would end up getting negative 29 newtons. And that would be fine, because it would be consistent with the way you defined the direction. The important thing is, if they're opposite directions, one of them is positive, one of them is negative. Now, one final thing with impulse before we move on here. I want to remind you that there's some qualitative implications of impulse as well, right? And those qualitative implications stem from an object that is either starting or stopping. This is the one we focused on the most, right? When an object is stopping, what do we typically want to do? Typically, yeah? Yeah, VF would be 0, but forget about the math of it right now. I just want to look at qualitatively what happens. When an object is stopping, the impulse is predetermined, right? No matter how you stop the object, the impulse is going to be the same no matter how it comes to a stop. Okay, let's say the guy stopped the soccer ball here. He cradles it, or he just sticks his foot out rigidly. The ball stops. The impulse is going to be the same. The key here is when you're stopping an object, you typically, when impulse is the same, you typically want to increase the stopping time. That's going to decrease the force. Right? Increase the stopping time, decrease the force. As opposed to when you're starting an object, impulse is not predetermined. Impulse is determined by you. So what you want to do here is increase probably both, the time of contact and the force. Because when you make time bigger, impulse is bigger. When you make force bigger, impulse is bigger. So when you're starting an object, both time and force affect impulse. But when you're stopping an object, the impulse is predetermined. It's time that affects force, then, inversely. Now, along with impulse goes, of course, force versus time graphs. And I told you guys when we did this the first time, you got to think of 3 words. 3 words should automatically come to your mind when you see this graph. And what are those 3 words? Yep. Good. Yeah, we know. Yeah, I know what you mean there. You know what you mean too. Area is equal to impulse. Good. So what you want to do, regardless of what we're asked for, is to find the area of this. Now, didn't photocopy very well for you guys, so it's pretty hard to see what the numbers are. So I'm going to help you out with that. On a test, it would be much clearer what the numbers were on it, where the grid lines are, and so on. We want to find the area of this. Find the area of this triangle. A1 will be 1/2 base times height. We got a base here of 1.75. It goes from 1 to 2.75. So the base would be 1.75, and the height, of course, is 10. That gives me an area of that triangle of 8.75. I know it's pretty hard to see that that's a 2.75. I wouldn't expect you to catch that on a test. It'd be much clearer. Well, then we've got another triangle down here. We'll call that A2. It's also a triangle. 1/2 of the base. I got the base here to be 1.25 because it's going from 2.75 to, no, it's not 1.25. It's just 0.25, isn't it? From 2.75 to 3. And That's going to mess up my answer here because on my answer sheet, I made it 1.75. My height is, what's my height here? Yep, 4, -4, right? Because it's below the x-axis. Remember, everything above, make positive. Everything below, make negative. Now, I don't have the answer there because I did it wrong on my answer key here. Let's do this now. 0.5 times 0.25 times -4 gives me -0.5. The fourth one here, or sorry, the third one, A3, is going to be equal to base times height. The base goes from 3 to 4, and the height is -4 again. And finally, the fourth one is a triangle, 1/2 base times height. The base is 1 because it goes from 4 to 5. The height is -4. That's going to give me -2. We got to add these up here. 8.75, subtract 0.5, subtract 2, and subtract 4 gives me 2.25. Newton seconds or kilograms meters per second. So think area equals impulse, and area above the x-axis is positive, area below the x-axis is negative. Now, we're not done yet. We don't even know what we're being asked for yet. We didn't even read the whole question. We just know that when we see this graph, we do this, right? Area equals impulse. We want to determine the car's velocity after 5 seconds. All we're going to do for this is say impulse is equal to m times delta v. Do not do this. Do not say impulse is F times t. Although it is technically true and valid, the force is all over the place here. And because the force is all over the place, what value are we going to use there, right? Just don't do it. Just don't use it. Use m times delta v. My mass is my impulse. Rearrange self for delta v here. My impulse is 2.25. My mass here is 0.075. And I got to recalculate this because I got it wrong the first time. I got an answer of 30 here. So my change in velocity is 30 meters per second. That's a pretty quick moving toy. This little girl is pushing this toy back and forth, and it's moving at 30 meters per second, 110 kilometers per hour. That's pretty impressive. What do we do after we did impulse, right? Qualitative impulse, starting, stopping an object, calculations involving impulse, watch the signs, graphs, area equals impulse. Next thing we did was collisions, right? Collisions and explosions. And when we do a collision or explosion, we're going to use this law of conservation of momentum, where the total momentum remains constant. Total momentum in the system remains constant. Individual things gain or lose, but the total will remain constant. Now, the total amount of momentum will remain constant if we have what? If we have, I'll give you a hint, if we have an isolated system. An isolated system is a system in which we have no external forces acting, right? System in which we have no external forces acting. Now, question number 3 that we see here, do we have external forces? Well, here's the deal. When we're solving one of these questions, when we're analyzing one of these problems, we want to look at just before and just after, immediately before and immediately after. And that gives us a chance to look at the collision or explosion without external forces having a chance to act. Like friction is going to be here, right? But if we look at immediately before and immediately after, friction hasn't had a chance to do anything. So we can still consider it to be an isolated system. So how do we solve a question involving conservation of momentum? Okay, again, pay attention to signs. If something is right, make it positive. If something is left, make it negative. Don't forget that. And then we just say PI equals PF. Total initial momentum, total final. We have 2 objects here. We're going to say M1 V1I, the momentum of object 1, plus M2 V2I, the momentum of object 2, equals Well, afterwards it says they head off as one object, so we're going to make it MVF. If they went as two objects, that would be fine. We just make it M1V1F plus M2V2F. Wouldn't be any harder, it's just one extra term, that's all. M1, we're going to say is 85 kilograms. V1I is 6 meters per second. M2, we're going to make 90 kilograms, and we're going to make him 7.5 meters per second. They head off as one, so the total mass afterwards is going to be 175, and the final velocity is this, right? Is that good? What am I missing? Good, the direction. I'm missing the fact that one of them is east, one of them is west. I don't really care which one you make negative, which one you make positive, but usually this one would be negative because it's to the west. As long as one is neg, one is positive, you're good to go. Again, if you miss that, the question's all wrong. Now, because it's written response on Friday, you would not get a 0 on the question, but you're not going to get full marks on the question either. We want to get 100 on this test. Not like 80 or 70. We want to get 100 here. All right, when we do the math on this, we're going to end up getting a final velocity of negative 0.943 meters per second. You guys okay with the rearranging of that? The algebra there? Now, what's the difference between that question where we have two cars colliding east and west, or sorry, two objects of two football players colliding east and west, versus the next question where we have two cars colliding, one's going west, one's going to the north? Yeah?
That's when you have to do the triangle.
Yeah, that's when you got to draw, we call it a situational diagram just to describe what's going on, and then we've got to resolve the vectors here. The good news is it's not all that hard in question number 4 because we're already at right angles. Let's draw the picture here. We got car number 1. It's 1,000 kilograms, traveling to the north at 36 kilometers per hour. In conservation of momentum, we don't actually have to convert to meters per second because units cancel. But we usually do, just as a matter of habit. 36 kilometers per hour works out to be 10 meters per second. So 1,000 kilograms, 10 meters per second to the north. We got another one that's going to the west. Call that car number 2. It's 1,200 kilograms, and it's got a velocity of 54 kilometers per hour, which in meters per second is 15 meters per second. How do we do that conversion, by the way? 54 kilometers per hour to meters per second? Good, divide by 3.6. Says they head off as one immediately afterwards. Doesn't really matter if they do or don't. Just makes it one less term if they go off as one object. X components, Y components. PI equals PF for both of them. Don't ever forget that. Okay, we need signs, positives and negatives, but when we've got a north and a west, we've got to go X and Y components as well. We can't just do what we did in question number 3. Let's say M1 V1I. That's actually 0. Why did I make that 0? Hamish? Good, because it's not on the x-axis. It's all on the y-axis. Plus 1,200 times negative 15. Made it negative 15 because it was to the left, right? Equals the combined mass is 2,200 times VF. And that one works out to be negative 8.1818. I mean, that's really the same question we just did, question number 3, except there is more to it, right? We did the X component in question number 3 because that's all there was. We've just done the X component in question number 4, but now we've got to do the Y because there's also a Y. This time we've got 1,000 times 10 plus 0. Why 0 for the second one here? This first one is all on the y-axis. The second one is nothing on the x-axis. So it's 0. We're looking at, sorry, on the y-axis, I should say. We're looking at the y-axis, not the x-axis now. The 10 is positive because it's going up. The total mass is 2,200 times VF. We solve for VF there, works out to be 4.54545 meters per second. And then we've got to combine them, right? We got to combine them by doing this. 8.18. We do that to the left because it worked out to be negative. Again, signs, positives, negatives. 8.18 to the left, 4.54545 upwards, and then the combined velocity will be right here. How do we find that velocity, or the speed, I should say? Evan? Yeah, Pythagorean theorem, we do, it works out to be 9.36 meters per second. And we find the angle using the inverse tan function of opposite over adjacent. And that works out to be, I got 29.1 degrees. And that's going to be north of west. We're measuring the angle from the west, north from the west, or north of west. Let's skip number 5 and go to number 6 here now. It says determine mathematically whether the collision in question 4 is elastic or inelastic. You guys remember the difference between elastic and inelastic? An elastic collision, Caitlin? Good. Kinetic energy is conserved. Now, there's a couple of things you got to be aware of there. I can't even talk and write at the same time. Kinetic energy is conserved. First of all, we're not talking about momentum anymore. What's the difference between, there's a difference in the equation between kinetic energy and momentum, but there's a fundamental difference between kinetic energy and momentum as well. Momentum is a vector, kinetic energy is a scalar. So I've been telling you this whole time, watch your signs, pay attention to directions. Is it positive because it's to the right, or is it negative because it's to the left? Is it X and Y components because we've got both north and west? Now we're not paying attention to any of that. If we're talking about kinetic energy, then the direction is irrelevant. Okay, we just do our thing with the speed as opposed to the velocity. Now, there's one more thing that I want you to remember here, elastic and inelastic collisions. If you have an elastic collision, the objects have got to bounce apart. Now, that doesn't mean just because they bounce apart that it's elastic, right? If they stick together, it's inelastic for sure. If they bounce apart, it's probably inelastic. It's not very often elastic. If they stick together, it's got to be inelastic. If they bounce apart, it's probably inelastic. But if they bounce apart, we've got to do a calculation to double check that. So that's what we're going to do here in question number 6. We know that this is going to be inelastic because they stick together, right? They stick together. It's got to be inelastic. But let's just double check it mathematically here. Let's say EKI equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Mass 1 is 1,000 kilograms. And v1 is 10, and we square that. Mass 2 is 1,200 kilograms. And v2 is 15. Wait a second. Shouldn't I do X and Y components here? No, because we're talking about kinetic energy. I needed to do it for momentum, not for kinetic energy. Oh, but wait, 15 is to the west, right? Should I make that negative 15? No, because we're talking about kinetic energy. It was important up here for momentum. It's not down here for kinetic energy. I solve for EKI, by the way, it works out to be 1. Can't read my writing there, but I think it's 1.85 times 10 to the 5. My final kinetic energy, there's only one object now. The mass of that object is 2,200 kilograms. And velocity is 9.3596 meters per second. I don't care that it was at 29 degrees north of west, because kinetic energy is a scalar. That mattered to me when I was calculating momentum, not for kinetic energy. This works out to be 9.64 times 10 to the 4 joules. So we knew this was inelastic because they stuck together. Right? Non-mathematically, it had to be inelastic. But mathematically, we've just shown that it's inelastic as well because kinetic energy is lost. that make sense? If they stick together, it's inelastic. If they bounce apart, it's probably inelastic, but not for sure. If kinetic energy is lost, it's inelastic. All right, let's take a look at number 5 now, which is repeat question number 4, but the 1,000-kilogram car is traveling at 30 degrees north of east. Right away, when I see this, you got to be thinking what? 5 words.
I hate funny angles.
That's 4 words, but close enough. Works for me. I don't like funny angles. Okay, I hate funny angles. I don't like funny angles, so we got to get rid of them, right? Let's draw our picture, our situational diagram, and then let's get rid of the funny angle here. We've got a 1,000-kilogram car traveling north of east. This is north of east. It's traveling at 36 kilometers per hour, which is 10 meters per second. 36 divided by 3.6. We got another car that's traveling to the west. Okay, that was car number 2. It's got a mass of 1,200 kilograms, and it's got a velocity of, what is that, 15 meters per second it was. Now, they're going to go off somewhere together. I don't know whether they're going to go off this way or this way. I'm thinking it's going to go this way. I'm not really sure. That's okay. Where I'm predicting they go is a little bit of a guess, an educated guess. But if I'm wrong on that, it's okay. I can't be wrong on this or this. I got to nail this one, these two. But my prediction for the final is just to help me visualize it. All right, I don't like funny angles, so let's get rid of it. Let's take it up here and put it out of its misery here. Here's 30 degrees. This is x, this is y, and this is 10 meters per second. So we're going to say cosine 30 degrees is equal to x over 10. X is going to end up being 8.66 meters per second. Sine 30 degrees is equal to y over 10. So the y component is going to end up being 5 meters per second. We always square it off there just to kind of separate it. And then sometimes we even redraw this. Sometimes we turn this into this. We got an x component here of 8.66 and a y component here of 5.0. Now the question is almost like number 4 was, right? We got 90-degree angles, which is nice. X component, y component. We're going to say 1,000 times 8.66, that's the x component of the first one, plus 1,200 times negative 15, okay, 8.66 positive because it's to the right, 15 negative because it's to the left, equals 2,200 times VF. Now, I don't have this one calculated, so bear with me for 1 second here. 1,000 times 8.66, subtract 1,200 times 15, and we divide that by 2,200. Gives me a value for VF of negative 4.245 meters per second. We do the same thing for the y component. 1,000 times 5, because the y component of the first one was 5, plus 0, because this is all x, equals 2,200 times VF. Solve for that, it's 6.8181, 6.8182 actually. And it's positive. Now it's just resolve it, right? Now is the easy part. 4.245 to the left. Again, signs. We're back to paying attention to direction now, right? Because we're talking about momentum, which is a vector. 6.8182. I don't have that calculator right now, and you know what? I'm not going to because I think you can do that. Sorry, yes, you're right. There is a mistake there. This was 1,000 times 5. I made it 15 in my calculator. What does that work out to be there? 2.273. So we're going to make this 2.273 now. Doesn't change our method, but it does, of course, change our answer. Solve for V there. I'm not going to bother doing that because I'll probably make another mistake. You can do the Pythagorean theorem, right? And the angle, of course, is found by the inverse tan function of opposite over adjacent, just like number 4 was. The only difference between this question and number 4 is this stuff up here. Okay, those 5 words. I don't like funny angles. Take it off to the side, put it out of its misery, turn it into a question number 4.